Okay, so hi everyone, welcome to the 42nd episode of the SFU Sports Analytics Virtual Seminar Series. Today we have Sana Arastehfar to discuss single agent behavior prediction in soccer using linear temporal logic. She has a master's degree. She recently defended in competing from Queen's University and a bachelor's degrees in computer software technology from Islamic Azad University, North Tehran branch, bioengineering, biomedical engineering, Amir Kabir University of Technology, Tehran Polytechnic. Her master's research was co-supervised by Drs. Christian Hughes in the School of Computing and by Catherine Pfaff in the Department of Mathematics, both of whom are here today. And it was funded in part by the CANSI, a collaborative research team in sports analytics. So in terms of the topic, so understanding and characterizing the playing behavior of soccer players is paramount for match analysis and team performance optimization. Therefore, the interpretability of such behavioral insights bears significant potential to enrich decision processes. Here we introduce a novel framework to extract long-standing behavior of a soccer player using temporal logic, which is abbreviated as LTL. LTL allows us to articulate time-varying events in the form of logical propositions that encompass temporal dynamics. Given a match represented as a sequence of frames encapsulating players and match information, our approach leverages handcrafted interpretable features characterizing the player's temporal dynamics. These temporal features are subsequently translated into logical propositions, effectively serving as inputs to a sophisticated Bayesian inference engine for LTL. This work presents a fundamental step towards leveraging LTL in the extraction of interpretable logical propositions, explaining a system of behaviors. So I will say that I think this is one of very few sort of computer science really inspired projects that we've had in our series. So we're looking forward to it. And I'm going to stop sharing my screen and turn it over to you. So thank you, Sana, for presenting.
Oh, thanks, Dave, for a lovely introduction. So, let me first. It's ready. Okay. Start.
Yep, please. Looks good.
Okay. Okay. Hello, everyone. I'm Sana, and I'm excited to talk to you about my master thesis, which is single agent behavior prediction in soccer using linear temporal logic, which explores the utility of linear temporal logic for predicting the behavior of a single soccer player. This thesis was co-supervised by Professors Christian Muse and Catherine Pfaff. So, in soccer, individual player impact is well documented, with behavior analysis crucial for various aspects like recruitment and strategy planning. Financially, soccer clubs invest heavily in recruitment, with millions spent annually, and coaches consider key behavioral factors when recruiting players, since understanding player behavior enhances decision making in strategy planning. Linear temporal logic, or LTL, offers a systematic way to articulate player behavior, allowing for a deeper understanding of how players contribute strategically to the game's outcome. So in this work, we present an approach leveraging LTL for sport analysis, aiming to comprehensively capture player behavior and its strategic implication. And ultimately, this could significantly impact player recruitment and role definition and strategy planning in soccer. So in this figure, we show the general pipeline of our framework. The whole process can be summarized as first extracting meaningful interpretable features for the player, which describe the player's movement, interactions with other players, and decision throughout the observed sequence. And then we translate these features into proper logical proposition through which the temporal logic framework can articulate and reason about the player's action and movement over time. Then we separate these sequences and extract the features into two meaningful distinct subsets as positive and negative sets. Finally, we use Bayes LTL framework, a Bayesian inference framework for extraction of that LTL specification, which best describe the player's behavior. For example, The attribute of the player possessing the ball will be translated into has ball, and then by the use of the separation function, the traces will be separated into positive and negative sets. And the LTL formula generated from the base LTL can be if the player is in offensive midfield right of the pitch, the player will have the ball. So by harnessing the soccer tracking data, which records the player and ball position throughout the match, we construct a framework to capture player behavior patterns and rationale behind their decision in varying on-field situations. As mentioned before, this involves transforming the data into logical statements, dividing the sequence based on the game dynamics, and applying the base LTL framework to extract the meaningful features expressed as LTL formulas. Our modular approach facilitates component enhancements, including the core Bayesian inference engine, ensuring adaptability and scalability. So our contribution lie in pioneering the use of the linear temporal logic, or LTL, in sport analytics, particularly in player behavior extraction, and proposing a systematic framework for behavior analysis with interchangeable components. So ultimately, our work offers a novel perspective on soccer analysis using logic and data to eliminate players' decision-making process on the field. So linear temporal logic, or LTL, was first introduced in 1977 by Amir Pinoli and others in the field of formal verification. LTL emerged as a branch of temporal logic, a field concerned with reasoning about time and temporal relations. Pinoli, a computer scientist and Turing Award laureate, I think, introduced temporal logic as a means to specify and verify the behavior of concurrent programs. So LTL is a formalism used to reason about time-dependent properties and behavior of dynamic system. It is a powerful tool for describing how different events and states unfold over time in a precise and systematic manner. So to be concise, we'd better lead off with some example of LTL specification to understand the difference between LTL and classical propositional logic. So classical propositional logic, do you see my laser point? Okay. So classical propositional logic might state a fact such as player A is at location X. So here there's no element of time in this proposition, and it expresses a fact which is supposed to be true regardless of time. However, LTL helps us incorporate the notation of time to build a more informative expressions. For instance, if we want to say at a time step in the future, player A will be at location X, LTL specification will be eventually player A is at location X. Or again, if we want to say the ball will always be on the pitch, the specification will be globally ball on the pitch. LTL also contains implicative proposition. For example, if the player is in location X, there will eventually be n teammates ahead of him or her, which we can show by globally player at location X, next eventually n teammates ahead of him or her. Base LTL is a Bayesian inference engine that we use in this thesis to extract LTL formulas, which was first introduced in 2019 by Joseph Kim, Christian Muse, and colleagues. To extract LTL formulas, base LTL received two sets of traces or sequences known as positive and negative sets, and find, if possible, the LTL formulas that best satisfy the sequence of the positive trace while not holding for the sequence of the negative sets. In this way, base LTL can find the LTL explanation for the behavioral difference between the two sets. So in this work, we directly use the available base LTL framework to find meaningful LTL formulas describing the behavior of a single player. Our proposed separation function are responsible for generating the positive and negative sets. And the base LTL extracts the LTL formula satisfied by the player in the positive sets and not satisfied by the player in the negative sets. For instance, we can figure out what the behavior is of a player when their team is in possession of the ball and in attacking formation, against the case that when they have lost the possession of the ball and they are in defensive formation. So now moving on to describe the first component of our framework, which is the dataset. In this work, we use the skill coordinate tracking dataset for the English Premier League season of 2022-2023. Each match contains metadata, including the overall outcome of the match, the home team, away team, team lineups, stadium, team size, and the pitch size. Each match comes with tracking data in the form of frames with intervals of 100 milliseconds, where each frame contains XY coordinates of all players in the pitch and XYZ coordinates of the ball. And for each match, each player and the ball has associated trackable ID. So now let's move on to data preparation. To enhance the accuracy for generating LTL formulas, continuous availability of the players and the ball coordinates, as well as team and player in possession of the ball are essential. But in multiple cases, as you can see in this video, this information is missing. We took the necessary pre-processing steps to fill out these informations. For balls missing information, we start with the assumption that the ball traverses piecewise linear paths. To fill the instances with missing ball coordinates, we employ interpolation during a game. So let's say ball coordinates within the time interval of 2 to 3 is missing, but the ball coordinates at the time 1 and 4 are known. Then the position of the ball during the interval of the 2 to 3 is determined via a linear interpolation of the position of the ball at the time 1 and 4. We follow the described procedure to fill out the missing ball coordinates throughout the game. And for the missing information on players and teams' ball position, we observe 3 possible cases where the possessor is unidentified. So first, where the possessing player is known while the possessing team is unknown, in which case it's fairly easy to assign the possessing player's team to the possessing team. And second, the possessing team is known, but the possessing player is unknown. And lastly, neither team nor player possession are known. So in the last 2 cases, we employ a Voronoi cell-based approach to find the possessing player. The case where the possessing team is known usually corresponds to the situation where a successful pass has occurred and the possessing team has remained unchanged. In that case, we assign the possession to the player on the possessing team whose Voronoi cell contains the ball. As you can see in the figure, the blue dot being the player and the orange dot or the yellow dot, I can't decide, is the ball, both in the same Voronoi cell. And so we can assign this player as the possessor of the ball. In this case, where neither is known, in the case that neither is known, the player's possession and the team, we use the same Voronoi diagram strategy with the difference that we include all the players and assign the possession to the player whose cell contains the ball. This case usually happens during intercepted passes. Once the possessing player is determined, finding the possessing team is trivial, the same as case 1. One important attribute that we compute in the pre-processing step is the visible polygon of the player at a particular instance. So to do so, we first introduce and compute a vector known as gaze vector, which is the addition of the player's movement vector and the player to ball vector, which is the arrow that we are seeing in this figure here, little one. Then we draw the line perpendicular to the gaze vector, so the visible polygon becomes the polygon resulted by the line segments and the pitch boundaries, which also contains the gaze vector. We use this visible polygon for future feature engineering steps too. The configuration of the opponent and teammates in the visible polygon of a player has an immediate effect on player's decision process. For example, imagine a counterattack situation where a player has received a long ball, sees nobody in his or her visible polygon. Then it's reasonable for the player to rushes towards the opponent's goal to create a serious opportunity to score a goal. So let's talk about the feature extraction and how they get translated into logical proposition throughout the proposed pipeline. After the pre-processing step, in order to fully leverage LTL, we start the feature engineering process to extract meaningful features from the environment. These features are transformed into logical propositions. The proposed engineered features are categorized to 3 groups: instance-based feature, temporal window-based feature, and spectral features. The important characteristic of all such features is that they are all human readable and interpretable, which is really important in our work. So they can be easily converted to logical propositions. Briefly, instance-based features are those computed based on the information of a single instance. And temporal and spectral features are use the information in the current and some previous instances to compute a feature and assign that to the end of that interval of time. So here we present the full list of the features which we use in our experiment, but for brevity, we go through a few in the next slide, which are the player's location, reachable teammates, progressive passing lane, expansion contraction, and principal movement. So first, let's go through instance-based features. The player's locations feature is a crucial feature. Since the player's location is given as a continuous XY coordinates, we need to discretize the pitch and determine the player's location in terms of the resulting discrete coordinates. We discretize the pitch into a 3x4 grid where each cell corresponds to a key role in actual soccer. So this figure illustrates such a grid for the case that the player is supposed to attack from left to right. If the attacking direction is reversed, the regions are mirrored vertically. And at each frame of the match, we can determine the location of the player in that 3x4 grid using the XY coordinates and translate the features into proper logical propositions, such as player at defensive left, which would be here, for example. Reachable teammates feature evaluates the number of reachable teammates at each instance of the game. We define reachability in terms of Voronoi cell adjacency. Simply put, Voronoi cell for a given point is the region of the space that is closest to that point when compared to all the other points. So two teammates are reachable if there exists a sequence of adjacent Voronoi cells between them, all occupied with teammates, of course. So, for example, the figure shown an instance of the game where the ball, the yellow dot here, is in the position of the blue player. Based on our definition, the player is in position of the ball, has 7 adjacent Voronoi cells showed in red color in this figure. And this translates into logical proposition that has 7 reachable teammates. In designing the progressive passing lane feature, we are looking for the number of teammates in the visible polygon of the player to whom the player can directly pass, considering the risk of an opponent intercepting that pass. So if there is no opponent closer to the passing lane than a certain threshold, we count the passing lane as a feasible one. Otherwise, it's considered risky. For example, if there are 5 such progressive passing lanes at a particular frame, a logical proposition is generated for the frame as 5 high-risk progressive passing lane. So here it's important to know that the flagging a passing lane as a high risk does not mean that the passing lane is not desirable, despite the negative sounding of the name. A player passing a ball while aware of the chance of the pass being intercepted by an opponent may be desirable tactic in various games since it can make an opportunity for the team. Expansion contraction is one of the temporal window-based features. It evaluates whether the K closest teammates are approaching the player, creating a more intense formation, which is demonstrated in the video on the right here, or diverging from the player, leading to a wider information, which you can see on the video on the left. So constructing this feature involves finding the average distance of the K closest teammates at the start and the end of intervals of a certain length. Using empirical data, we have set the interval length to 2 seconds and set the K to 5, accounting for 5 closest teammates. And lastly, a spectral-based feature. The main objective of using spectral features is to find features that describe the behavior of the player when they are not directly available by looking at the temporal data. So here we have introduced one feature, principal direction of movement, which follows the same procedure as principal component analysis algorithm to get information on the player's general and dominant movement direction within a certain interval, of course. So to generate the logical proposition, we look at the angle of the principal movement direction and classify the type of the movement. For example, if the player's dominant movement is of a progressive direction angle, it corresponding logical proposition would be player is at progressive direction. So here the player angle is at progressive, and as you can see here on this circle. So that would be Arizona. Yeah. Okay. Having the features and their corresponding logical proposition at hand, the next step is to devise a separation function, which can meaningfully separate the whole trace of a frame into two sets with different properties. These two disjoint sets are necessary so that the base LTL engine can extract a meaningful LTL formula from the traces. We have designed three different separation functions called team position, attack defense, and passing style separation function. But here we only elaborate on one separation function two separation functions as an example. Attack defense separation function is designed to separate player traces into positive sets in which the player's team is attacking and negative sets in which the player's team is defending. So to establish the attack and defense modes, we define specific criteria for each. We introduce penetration mode of attack detection, which you can see here on this left hand side video. If the player's team carries the bar over half of the pitch towards the opponent's goal, with a distance over 45 meters, it indicates a penetrative attack. Alternatively, we introduce concentration mode for the attack detection on the right-hand side of this video, in which we shift our focus to the player's team's ball position in the opponent's defensive quarter. So we do not care about like the penetration distance. We just want to capture the attacking persistence. Similarly, in defense detection, the retreat mode examines the opponent's team ball possession behavior too. If the player's team retreats towards its half of the pitch while not in possession of the ball, which might indicate a defensive stance, it highlights a strategical movement to protect their goal, which you can see here on the left-hand side video. And similar to the concentration mode in attack, the concentration mode in defense prioritize the opponent's team presence in the defensive quarter of a player's team, irrespective of the overall retreat distance. Moving on to passing style separation function, the primary objective of this function is to separate traces based on two distinct passing style. The differentiation of passing styles is accomplished using k-means clustering. So the assumption in building this separation function is that the instance where the position of the ball is interpolated and where the team position is known, but the player position remains unknown, may coincide with passing events. As can be seen in this video, the ball being passed between the blue players, which indicates that the possessing team remains the same, but the player position is not. So the ball is like moving between these blue players, and the possessing team is known, but we cannot assign in the data set. There is no indication of like who is possessing the ball, which player is possessing the ball, but we know that the blue team has the ball. So the first step to extract a single pass from the tracking data and then find continuous uninterrupted sequence of passes for each team. Having a clear representation of passing sequence and its constituted passes, we can introduce the features which account for different passing styles. So from each passing sequence, we extract the following features: number of consecutive passes, average pass distance, average pass duration, coverage area of passing sequence, center of concentration, and average ball height. After introducing the different passing styles feature, we we proceed to apply the k-means clustering algorithm to the set of the feature vectors of the passing sequence in order to separate the collection of the passing sequences into distinctive, meaningful sets. In this particular analysis, we use two clusters, allowing us to distinguish between the positive and negative traces for each passing style and extract players' behavior accordingly. Once the clustering is complete, we obtain the center of each cluster and translate the center using the feature description. Here we only go through two of these features, coverage area of the passing sequence and the center of concentration, because I feel like the other features were self-explanatory. Okay, coverage area. The coverage area of pass sequence. So in the passing sequence, we define the coverage area of the passing sequence as the area of the convex hull of the ball positions in the passing sequence, which determines the extent of the pitch utilized. So as you can see in the figure, the coverage area could serve as a feature for the passing style. Each blue spot represents a stopping point of the ball during the represented passing sequence. The wider the convex hull, and subsequently the greater the area used, implies a wider and braver style of passing, like these three convex hulls. While a narrower convex hull indicates a more conservative passing style. The center of concentration. Okay, this feature involves obtaining the coordinates of the ball across all passing sequence and calculates the average of these coordinates. This feature offers insights into the symmetry of passes among the players. If the center of concentration is positioned at the center of the mass of the ball's stopping point, it indicates a balanced distribution of the passes amongst the player and equitable involvement of the players during that passing sequence. So the yellow rectangular is the heat map. This figure is the heat map of all of the passing sequences during a game. And as you can see, this yellow rectangular is showing us that most of the passes happened in that part of the pitch. So more precisely, if in a passing sequence, all involved players touch the ball in the same number of times, their corresponding location appear the same number of times in the averaging process, and hence the center of concentration overlaps with the center of mass of the player's location, or the ball's stopping point also. And if the contributors of one or more players are more than the others, contributions of the one or more players are more than the others, their corresponding locations appear more often in the average process, hence absorbing the center of concentration towards the location of more involved player. It means that if the center of the concentration is closer to a particular player, those players were primarily responsible for distributing the ball. Following the methodology, we analyzed the generated LTL formulas, descriptive and discriminative attributes to evaluate their efficacy in providing insightful information about the player's behavior. So in general, we conduct three different experiments. To evaluate the model, we arbitrarily considered one player of the Manchester City Football Club, which we refer as to player A. We use the attack, defense, penetration, retraction mode separation function, and we let the Bayes LTL method generate 20 formulas with the highest score for each separation function. The scoring of the LTL formulas for contrastive explanation involves assigning a probability score to each subformula, reflecting the likelihood of that subformula being responsible for the observed behavior. So this video is a match from start to end, showing the traces for a single player here on the top left side, and generated formula on the top right hand side. So the traces that we have here will be given to base LTL, and base LTL will generate these formulas. Okay, as the first experiment, we produce sample formulas by analyzing a match between Man City and Chelsea, focusing on player A. So this table demonstrates the example LTL formulas extracted from the match. Take the second formula as an example, which translates to when the player is at the location defensive midfielder on the right side of the pitch, there will be 6 teammates ahead. So you can see that here in this instance of the play 2, our player is here, player A is here, and he has 6 reachable teammates. And players A's official role is attacking midfielder. This formula reveals that when the player A comes back into defensive position, his teammates are rushing towards the opponent's goal. This shows that the player A could have a playmaking role in the match. Here we provide a systematic approach to determine the usefulness of a particular feature. So we remove one feature at a time and calculate the average score of generated formulas of the type response and stability, and sometimes before. If removing the feature leads to a lower average score of the desired formula, it suggests that the feature's usefulness. So we compare the average score of the top 20 LTL formulas generated before and after feature extraction with different separation functions. Never talked this long in my life. Okay, so moving on. So in this table, the blue scored color suggests that for the specific separation function, dropping a feature lowers the average score of the LTL formulas, and the red color denotes that the specific separation function, the omitted feature, resulted in a higher average score. From this table for player A, we can spot that several features whose removal consistently drop the LTL formula average score regardless of the separation function and chosen player. These features include player's location, opponent density, has ball, reachable teammates, backward passing lane, and expansion and contraction. One can think of these features as the most effective features. However, it is not the same for the teammates density. Rather, we can say that the reachable teammates feature has a more pronounced impact on the player's behavior compared to the teammates density. And also, moreover, we could pick a specific separation function and determine the impact of the different features when that particular separation function is used. For instance, the teammates density feature has a direct impact on the LTL scores when the separation function is passing style, attack defense with penetration and retreat mode, or attack defense with penetration and contraction mode. So remember the constructive explanation behavior of the base LTL. This implies that for different passing styles and different attack defense strategy, the number of teammates inside the player's visible polygon directly influence the player's behavior. And another example fact that can be observed from the table is that the progressive passing lane features are influential for the player's behavior when we are analyzing behavior in terms of different passing style. So in general, we can observe that the effect of features is directly influenced by the player and separation function. In fact, this could be the reason for the increase in average score in particular cases. As the third and the last experiment, we conduct an empirical investigation to assess the discriminative efficacy of the generated LTL formulas. We extract the LTL formulas for a target player to achieve this objective using 3 separation functions introduced before. And subsequently, we incorporate the traces of 3 other anonymous players alongside of our target player. For each trace attributed to every player, we count how many LTL formulas are satisfied. We expect that the number of satisfied LTL formulas for the trace of the target player, the player for whom we initially extracted the formula, exceed the number of satisfied formulas for traces of other players. So in this table, we can see that our framework has successfully distinguished between the players given their respective sequence. So let's dive a bit more into this. So each cell in this table shows a list of um, of each whose elements is the number of satisfied LTL formulas for a player. Since we have 4 players in our experiment, each list has 4 elements. So in our experiments for player A, initial formulas for this player are extracted. Then we feed the traces of player A, B, C, and D into the LTL framework and count the number of formulas that were satisfied over each trace. For the experiments on player A, we expect that the first element of the list is larger than the other elements, implying that the extracted LTL formulas are well tailored only for player A. So as you can see in passing style, the scenario where the separation function is the passing style, we can see that the 20 formulas, LTL formulas, 13 of them align with players A's choices, 2 only with players B, 9 with player C, and 1 with player D. As you can see, we were expecting this and the model delivered. So we repeat the experiments for other separation functions, including attack defense with penetration and contraction mode, and attack defense with contraction mode, and also team position. So upon closer examination of the attack defense separation function with a concentration attack and retraction defense mode, a large disparity between positive and negative traces become noticeable. So in some cases, the separation function only results in the positive traces and output no negative traces, which makes it impossible for the base LTL to draw reliable outcome. So this suggests that the ineffectiveness of this mode of attack defense separation function as it fails to produce insightful distinctions. In summary, player behavior learning is a crucial task in sport analysis, which greatly impacts the high-level decision process of for coaches and team performance analysis. In this work, we propose a novel framework for a single player's behavior extraction based on LTL linear temporal logic, or LTL, sorry. We showed this approach is advantageous in providing interpretable description of a player's behavior throughout a match. We provide a complete end-to-end framework, which enables us to effectively employ the method in real-world scenario. And we believe that this work is the first attempt towards facilitating a vast research field of utilizing LTL for behavior analysis and shows potential for tremendous improvement. And there are various avenues to further expand this framework. To name a few, we only here handcrafted 16 features, while one could think of more sophisticated yet interpretable features to be used as the input of LTL engine. And we're devising a strategy for better translating the output of LTL expressions into practical insights to provide coaches, analysts, and other pertinent stakeholders with actionable information to inform decision-making process. And some could pursue an enhanced gaze tracking methodology predicted upon more informative, rich data resources. This is currently a focused area of research, and more sophisticated approaches can be incorporated in this work too. And also investigate the viability of employing an events-based separation function. Such events can be like goal, dribbling, shooting, etc. A prospect facilitated by the availability of pertinent events-related data. And that's it. Thank you for listening. And any questions? I'm here to answer.
Great. Thanks, Sana, for your very clearly explained talk. We appreciate that. Okay, so we'll open it up to questions from the audience. I think crowd size, we can just unmute and speak into the mic.
Oh, we should credit, where did you get your data from, Sana?
Oh yeah, Skill Corner data set. I said it in the when I tried to talk
So
about the
thank
data
you
set.
to
Corner.
Skill
Yeah,
Corner
thank
for
you.
the data
Thank
set.
you. Yeah, we got the tracking data set from Skill Corner. Yeah.
Skill Corner, is that what you said?
Pardon?
Sorry, did you say Skill Corner? What's
Yeah,
the
yeah.
name of the company? Okay, great. My microphone wasn't working very well there. Okay, so yeah, questions from the audience.
Hi, Sana. I have a question regarding the data. So, like, how many seasons of data do you have for the tracking data?
We just had the English Premier League from 2022 to 2023, so it would be 4. Yeah.
Okay, that's a lot of data. And I also have a question regarding I forgot which slide it is, but you mentioned a couple of features, including one called the average ball height.
Oh, okay. Let me bring it up. Here it is.
Yeah. So for the average ball head, can you like provide more details about it? Do you mean that you also have like kind of three-dimensional data?
So we for the ball we had X, Y, Z coordinates, and we added this feature because it would have given us like this feature would have added to the separation function, as in like would the player receive a long ball or like it's a short pass. So we only could use it for that. And as you can see in this slide, the average ball height was 30. Yeah, the highest was 30, and no, the highest was, what is it here? 30 of the shoots in the whole match was less than 1 meter. So not such long balls.
So like for this ball head data, does it have the same frequency as the player's locations?
What do you mean by frequencies?
It's like, for example, if your tracking data record the player's locations, say like 30 times per second, like does the ball head is recorded at the same
Yes,
frequency? Wow,
yes, yes. Everything is recorded at the same frequency.
I see.
Except
Like,
for some of the information that are missing. But like it's fairly normal.
wow, that's impressive. Okay, so like to obtain the data, do we need to contact the company or?
Yes,
Mhm.
yes, it's
Okay.
what I did.
Okay.
Well, we can, if you email, we can get you in touch with, there is a contact that for students, they will, you can put in a proposal and they will, often, let you use their, data for research purposes, yeah.
Okay. Thank you so much. Thank you. And I like your talk a lot. Thank you.
Yeah. Hi, Christian. I just saw you.
Great. Any questions from the audience? And maybe while we're waiting, so with all these features, I mean, are you looking at game by game, and is there like, can you look at on a season long basis? I mean, are players' features changing over time, and is this something that can be, are these features something that can be like manipulated by a coach, or like how do you make actionable decisions based on the analysis that you have?
Um, so this is a great avenue for somebody who wants to expand on this work. We only laid the foundation of like we only looked to like a year of I don't know, games. And we were trying to propose a more general features that can be used in all of the games, and wasn't like particular to one coach or one single player. So everybody can use it, and we can see that how would this framework work and like be applicable in the sport analysis.
So one thing, if I can like offer an example, if you could see, so one thing you could use this for would be to see, you know, in these kinds of circumstances, these players are more likely to do blah blah blah. And with that kind of information, you could decide, well, that's not what I want as a coach. And then so it could pinpoint things.
Yeah.
You know, it can pinpoint behaviors. Would you say that's correct, Santa?
That too, yeah.
Yeah. Which would then be actionable in terms of understanding how a player is making decisions and how they're behaving. And then, you know, it'd be up to the coach to decide how to alter that.
So did you like look at any players in this way? You know, sort of let it with an eye to either profile them or critically examine their performances?
We had like for each of these for generating LTL formulas, you have to like focus on just one player at each time. So we did that, but like we did not examine them for how a coach would use this information, because we needed a coach to
Yeah, sure.
to
Yeah,
lead us in the right direction, right?
of course.
Yeah. But like there are tons of LTL formulas that they can like be translated into actionable strategies, maybe.
Okay, thank you.
I think so. I think we focus more on seeing that this was working.
Yeah.
To identify, you know, figuring out, you know, extracting features and figuring out whether this was working to create formulas and formulas that were different for different players, and things like this. You know, a next step could definitely be then to analyze particular players and their behavior. And then the next step after that could be to try to impact it. But yeah.
Exactly, like it's one of the future works in our in this thesis is that like people can come and translate the LTL formulas effectively so that the coaches can like use them. And also like this is a foundation of like using LTL as a behavior analysis in sports, right? So a lot of people can come and add to this thesis.
Right. So if I can summarize, so like this work, I guess is just it's a methodological work. You've developed the method. I guess you know, and sorry, you know, it's my unfamiliarity with the area is largely the source of my questions here. But so you know, what is it like? What defines how like that the method is working? Like what part of your analysis showed that yeah, this is indeed working? And you know, can you even say, can you go beyond that and say yes, this is a valid analysis of this, you know, of the game, or this method is validly doing what we want it to be doing?
Yeah, so the experiments parts, like only if we look at the LTL formulas, we can see that these formulas are giving us insights about like how a player would react in a certain situation. And then if you can like look at the discriminative power of it, like it can separate the players like how they behave. This player behave differently than this player. So I feel like these two experiments answer your question, that like we are confident that this work can be used in a real world application.
Okay, thanks.
An informal test would be that one of her committee members correctly guessed who one of the players were based on his
Yes.
formulas.
Yes, that happened. I forgot.
Well, that's that is a good accomplishment for the method, certainly. Okay, any other questions from the audience?
So should we mention, I wanted to, as her, as one of her supervisors, I wanted to slip in a little bit that, so now that Senna has successfully defended her thesis, she is actually on the job market. If you are impressed with her and what she's doing, she is actually looking for a job now. So.
Thank you.
Right on. So are you looking for a sports analytics job ideally, or more general data analysis?
I'm looking into sport analysis actually is fun. My roommate is like pushing me towards it because he wants a job after me in that field. But sport analysis and machine learning engineering, yeah, is my goal in general.
All right. Well, good luck in your pursuit there, and
Thanks.
hopefully something will come your way soon. Okay, well, I guess I'm gonna just say thanks very much, Sana, and to Catherine and Christian for joining us and to share your very interesting work in this area. And thank you everyone for joining, and we'll see you next month.
Thanks all.